Hi, so we're doing the 2013 scholarship stats paper and we're doing question 3c. So if you'd like to see a video going over question 3a and b, they're both on YouTube as well, so you can check them out if you want to. So question 3c. A dairy factory produces bags of milk powder which are filled by an automated machine. On average, the filling machine underfills 6 bags per hour. Some factory workers, called operators, are used to top up any underfilled bags. Each operator can, in addition to their regular work, top up at most 2 bags every hour. So each one can top up at most 2 bags every hour. The company wants to make sure that in the long run, no bags are left underfilled at least 90% of the time. So no bags are left underfilled at least 90% of the time. What does that mean? Well, let's unpack that a wee bit. The best way to approach this is to start by looking at what is the event. So what's the kind of the event that the sentence is all about? So pause the video and see if you can circle what the event is. The event is the scenario where no bags are left underfilled. So that's our event that we're interested in. And the probability of that event needs to be at least 0.9, at least 90%. So that what we just did there, that's a really good exam technique in scholarship stats. When you get a kind of confusing or complex statement, which you'll get, that is scholarship, start by saying to yourself, what is the event? Be clear on that. Okay, now the instructions. First one, calculate. Always underline the verbs. Calculate the smallest number of operators the company requires. Okay. Second one, in your answer, justify. So we've got calculate and justify. Justify the choice of any probability model. So because we're doing scholarship and the topics are all mixed up, that's the first thing we've got to think about. And what sort of achievement standard content are we looking at? Well, the big clue here is probability model. So we're either looking at probability or probability distributions, or both. So let's have a think about which probability distribution might be appropriate here. Okay, first thing we need to do is think, what's the variable? So what's the numerical variable here? Well, there's kind of two things they've asked about. Originally we're told we're interested in the number of underfilled bags. We're also then told we want to know the smallest number of operators. Okay, in either case, we're counting. So number of underfilled bags, number of operators, they're discrete variables, aren't they? So we're probably going to be looking at the binomial or the Poisson distribution. So we sort of pencil that in. Okay, so how do we know the difference? Well, binomial we use when it's out of a fixed number of trials with a constant probability of success in each trial. Poisson we use when the discrete event is occurring within a continuous interval. Okay, so which one is it? Well, it's per hour. So we don't have a maximum number of bags we're checking, so it's per interval. So it must be Poisson. Well, it can't be binomial, can it? And we can look further into the assumptions required a bit later on, but we want to get started on this question. So let's go with Poisson. Okay, so what are we going to work with here? Are we going to work with the number of bags per hour as an X variable, or are we going to work at the number of operators? Well, it all starts with the number of bags, doesn't it? Because it says that on average the filling machine underfills 6 bags per hour. The question about the operators is that we know operators can top up the bags, but it all depends on the number of bags actually underfilled in the first place. So what we're really interested in is the number of bags. So our variable X is going to be the number of underfilled bags per hour. X has to be the number of underfilled bags per hour because the number of ones that get topped up still kind of depends on the number that are underfilled in the first place, doesn't it? So we're going to start with that. Okay, so we want to know the x value where that relates to a probability of 0.9. This is the tricky part of this question, and this is where we really need to take our time. So we know that the mean number of bags underfilled per hour is 6, and we write the mean as lambda. So lambda per hour equals 6 underfilled. Okay, and with Poisson, lambda is our mean and it's our variance too, isn't it? So let's start having a wee bit of a play. Grab your graphics calculator out, and we know that we need to find, essentially we've got to end up finding the number of operators, but let's just start with the number of bags per hour. So what number of bags per hour would be the maximum that would be underfilled 90% of the time? So would it be 0, 1, 2, 3, 4, 5? We don't know how many yet. So let's grab our graphics calculator and have a play. So menu, stat, distribution, F6, Poisson, and we don't want particular values, we want cumulative, we want range of values. Okay, so our mean, what's our mean? It's 6. And let's start with let's find the probability of getting no bags underfilled in the first place. What would that be? Very low, so 0.00248. What about 1? So exit, and let's change the x to 1. So this is going to be 1 or less bags underfilled per hour. 0.017. Okay, what about 2? So 2 or less bags underfilled per hour. Here we go. 0.06197. Okay, so it's getting high, but it's still pretty low. So we're starting to get an idea. Let's go back and look at the question again so we can get our heads around it. Okay, so really, obviously the goal here is to minimize the number of bags that are left underfilled, and we're told there's 6 per hour. So we're trying to get an idea, if we were looking at this 0.9, we want no bags left underfilled at least 90% of the time after the top-ups have occurred. So let's find out the number of the minimum number of bags that would be underfilled 90% of the time, 90% of hours. So that means how far up here would we have to go to get to 90%? Now, if the mean is 6, that means we can be pretty sure, we can safely assume that the 90% mark would definitely be above 6, wouldn't it? Because 6 is the mean. So let's start with 7. So grab our graphics calculator and let's change it to 7. And we're expecting it to be over 50% now, wouldn't it? So this is that 7 or less bags are left, well, 7 or less bags are underfilled in an hour. And it's 74%, okay? So let's make a wee bit of a table to record this information. So number of bags underfilled by the machine, and let's call that U for underfilled. Okay, now in the right hand column we're going to put the probability of getting that number or less underfilled. So less than or equal to, the x is less than or equal to U. Okay, so if we start with what we already worked out, which was the probability for 7 or less being underfilled was 0.74397, so 0.744. So in here, 0.74. Okay, now we need that probability to be up to, well, it needs to be over 0.9, doesn't it? Because the question said for it to be more than 0.9, well, at least 0.9, okay, at least 90%. So let's try 8. Okay, so graphics calculator out, and we'll change that to 8. And we get 0.847. Is that high enough? No, it's still below 90%. So 0.847. Okay, let's try 9. So changing it to x value to 9. Whoa, and there we go. So it's 0.916 now. So it's just broken over that 90% mark. Okay, and going back to the question again, we can just to check. Yeah, we need it to be at least 90% of the time. So that means the number of bags that would be underfilled by the machine in an hour, at least 90% of the time, would be 9. So 8 or less are underfilled 84.7% of the time. 9 or less bags are underfilled over 90% of the time. So 9 is our critical value. Now, the goal here, though, if we go back to the question, the goal is to find the smallest number of operators required so that no bags are left underfilled. So if no bags are left underfilled at least 90% of the time, how many have to be topped up by an operator? Well, the answer is, of course, 9 have to be. So we need to find out how many operators would need to be on duty to cover those 9 that are unfilled. So let's go back, and we're told a couple of extra things. We're told that each operator can top up at most 2 bags every hour. So if we assume that they manage to top up those 2 bags per hour, how many operators would we have to employ on the floor to cover those 9? So if we go with the 2, obviously 4 operators isn't going to be enough, because 4 times 2 doesn't take us to 9. So we need to have 5 operators employed. Okay, so we need 5. So conclusion is, well, let's go back and actually check that we're answering the question exactly right. So calculate the smallest number of operators the company requires. Well, therefore, the smallest number of operators to make sure that no bags are left underfilled at least 90% of the time is 5. So therefore, at least 5 operators to ensure that no bags are left underfilled, at least 90% of the time. And that's our verdict. Now, there was one more instruction too, and that was, in your answer, justify the choice of any probability model used. So why is Poisson appropriate? A good acronym for the Poisson distribution is RIPS. RIPS. And this gives us our 4 conditions needed. So the R stands for random, the I stands for independent, the P stands for proportional, and the S stands for simultaneous, or really it's that events cannot occur simultaneously, so not simultaneous. Okay, so there's RIPS. Now, in this situation, the overriding one, of course, is that for Poisson, we have to be dealing with discrete events in a continuous interval, and so we sort of mentioned that back at the start, and we should actually add that in at the beginning. So discrete event, number of bags underfilled, context, in a continuous, or within a continuous interval, an hour. Again, we've got the context in there. Good, so we've sort of covered that one. The RIPS one, so random, we're assuming that what are we assuming? We're assuming that the occurrence of underfilled bags is at random. Let's see if they've said anything in the question about that. No, they haven't told us that it occurs at random, so therefore we need to say that that's an assumption that we're making, because we don't know. So assuming that underfilled bags occur at random. So we've got the context there of underfilled bags. Independent. We're not told. Well, let's just again double check if they said anything about whether the occurrence of underfilled bags is independent. No. So therefore, again, independence is an assumption. So we need to point out that we're assuming. So we're assuming that the occurrences of underfilled bags are independent. In other words, that if one bag is underfilled, it doesn't alter the likelihood of another one then being underfilled as well. Okay, proportional. Doesn't really come into this because we're sort of dealing with per hour the whole time. So what proportional means is that we're assuming that the mean number of bags underfilled is proportional to the time interval. So it's proportional to the length of time. So assuming number of underfilled bags is proportional to length of time. And simultaneously means that when we use the Poisson model, we're assuming you can't get more than one occurrence of your event at the same time. So you can't get sort of double ups. And so that's not an assumption, that's a fact, because it's assuming there's only one bag can come off the production line at a time. And so you're obviously not going to get two underfilled bags together at the same time. So that one's okay. Can't get more than one bag being underfilled at the same time. So just in conclusion, what's that saying? Well, we should have really put this at the top as a bit of a heading, eh? So the heading is use of the Poisson model here. So use of the Poisson model in this context means that we're assuming blah blah blah. So just to point out to the examiner that what this is about. Cool. So let's actually look at, firstly we'll just check we've answered the question, and then we'll have a look at the marking schedule to finish off. So we were asked to calculate the smallest number of operators the company requires. Have we done that? Yeah, we need at least 5. So we've done that. And then second, have we justified our choice of probability model? Yeah, we've named the Poisson discrete event in a continuous interval in context, and we've talked about how the 4 requirements are met, or what we're assuming. So we've done those 2 things. So let's actually see how we would have gone. So to get hold of the assessment schedule, you can just go to the NZQA website and go to mathematics page and then scholarship statistics, and you can download it. So just a couple of general principles. Ignore incorrect answers of alongside correct answers. The exception is contradictory statements. And 2, ignore minor copying errors. So let's go down and look at this question. Okay, so question 3c, evidence. So use Poisson with mean 6. We did that. X is number of bags that need topping up in an hour we require. So see, that was the first thing that we did as well. We defined what the variable was, X. And that has to be at least 0.9. The probability of getting less than or equal to that number has to be at least 0.9. We keep adding Poisson the probabilities under mean equals 6 until 0.9 is passed, which is what we did. And we got to 9. 9 bags require topping up at least 90% of the time. So the smallest number of operators is 5. 5 times 2 takes us over 9. We use Poisson here as the number of underfilled bags per hour occurs randomly and independently. We assume that anyway. Events don't occur simultaneously. Also, the number of underfilled bags is proportional to the time interval. Note, answer can be expressed to 3 decimal places as 0.103. Not sure what that means. And can use normal approximation to Poisson with mean 6 and standard deviation 2.45. In other words, what they're saying is if you wanted to, you could have approximated this with a normal distribution. But there's no need to. It's actually faster just to use your graphics calculator. And judgment. So this question, you could get up to outstanding level 1. O for outstanding. Correct answer plus justification of 3 points. So that means out of the 4 conditions needed to use the Poisson distribution. So if you stick to RIPS, R-I-P-S, you always will cover those 4 points. Okay, for using the Poisson distribution, must include proportional justification. S, scholarship level, just getting the correct answer, so a 5. P, partial, some evidence of correct calculation, e.g. choice of Poisson with part calculation of, or some justification of Poisson distribution. All right, cool. One other wee thing on that question, by the way, to get our answer, there is a shortcut. If you've got the latest sort of versions of the graphics calculator, which is, I don't think this one is. See here, you've only got P, PD, and PCD. If you've got a newer version that has P inverse, Poisson inverse, you could have actually just typed in the value of 0.9, and it would have spat out the answer of the fact that X has to be 9. So if you've got that feature built in, it's a wee bit of a shortcut. Thanks for listening. See ya.